Okay, so this is the first lecture, which is to replace the lecture for Monday, September 11th. You will recall that I am traveling to Washington, D.C. and am unable to be in class on that Monday or Wednesday. So to set the scene, let's just recall where we're at. We're in the process of talking about different ways of viewing a random field. And the first way we talked about it was through a model representation. And this is pretty familiar from other statistics classes. We're going to think of our data arising from structure plus error. Of course, what's interesting in a spatial statistics class is that the error piece has spatial structure. And so the mean piece does not fully account for everything that's going on spatially, and what's left over, what we need to sponge up, has remaining spatial structure that we will turn around and estimate and model. We then talked about the convolution representation, and this was the idea of generating a random process by starting with a spatial white noise process and then using a kernel to smooth that spatial white noise over the study region. And what we saw was that the kernel completely determined the dependent structure, at least in terms of the covariance function. So that the kernel and the covariance function, there was this one-to-one relationship between those. And now we turn our attention to the spectral representation, where we're going to view a random field through its Fourier transformation, or through its Fourier transform, I should say, which should give us some information about the frequencies we're seeing in the spatial field. And that may be hard to envision, but well, we'll get there. So I'm jumping ahead here to page 51 of the notes, and this follows along with the Schabenberger and Gotway book, so we're looking at section 2.5.1. Eventually we need to do a Fourier transform of this random thing, but we're going to start off by talking about the Fourier transform, or the spectral representation of deterministic functions. And then once we understand that, we'll jump into how do we do it for this random thing. We're going to do this in the deterministic piece in two steps. As I said earlier, Fourier transformation talks about decomposing a function down to its frequencies. And so that's most easily seen if you start with a periodic function. And so in that case, the Fourier analysis is actually a Fourier series. And then we'll extend these ideas to a Fourier transform, which is applied to non-periodic functions. And just as a reminder, the idea is that we, of any transformation, is that we start with a function and we recode it in a way that it's perhaps more useful to do usually math things on the transformed function than on the original function. But what's important is that all of the information of the original function is retained in the transformed function. It's just, it may be harder to see, but it's all there. That's transform in general. Fourier transform, as we said, is breaking it into its frequencies. And so that's why we're going to start with periodic functions. Okay, so we begin with the definition of a periodic function. And basically a periodic function is one that repeats every distance p. So p is going to be the period, and the way we say it repeats is through this relationship here, where you can see that when t takes on integer values, the argument of the function is increasing by some multiple of p, and what we're saying here in this box is that the value of the function is the same. And so if we start here at time s. What we're looking at in this picture is a simple periodic function. I've got this sawtooth function in blue, and I can look at any location s. That's what I've done here. If I jump a distance of one period, the period of this sawtooth function is 4, notice that the value of the function at s plus 4 is the same as the value of the function back here at s. And of course, if I jump back one period, the value of the function at s minus 4 is the same as the value of the function at s. And that, of course, would continue if we looked further and further at different multiples of 4. So the next thing that Schabenberger and Gotway are going to do is they're going to introduce Fourier analysis, and they're actually going to change notation a little bit. They're going to, up here, we were saying that P was the period, but P now is going to denote the half period, and that's really just for convenience. So our period, we're going to start with a function with period 2p, assuming that it's integrable over the interval from negative p to p. You can see, oh, this is why they chose p to be the half-width. We're going to look at the function only between negative p and p. That's a total distance of 2p, and that gives us all the information about the function because it's periodic every 2p, right? So that's why this change in the definition of p has occurred. Okay, so we start with a periodic function with period 2p, and this is what Schabenberger and Gotway say. They say that the function that we start with can be written in this form here, which is a sum of basically cosine waves and sine waves. So and those cosine waves and sine waves have been chosen with particular frequencies, and the frequencies are ones which repeat every 2p. We're going to start with a function with the lowest frequency, the longest wave is going to be 2p, and then we're going to cut it in half, and we're going to cut it in half again, and we're going to cut it in half again, and the what we're going to do is we're going to add higher and higher frequency waves. So what this top half says here is that our original function can be written as a combination of a constant term and sine waves and cosine waves with increasing frequencies. The ANs and the BNs, these coefficients, are going to determine the magnitude of the cosine waves and sine waves. And so what we need is a recipe for obtaining those ANs and BNs, and that's given down here. It says that the right coefficient AN is obtained by integrating the original function with respect to the cosine written this way. Bn, of course, is with the sine. And so there is a lot in this statement. In fact, there's two pieces of it, and I think the first piece is the second half. So that's why I say part 1 down here. Part 1 is the transform. We're starting with the original function f, and what we're doing is we're recoding it into coefficients an and bn. So the difference between a Fourier series and a Fourier transform, that we talked about a transform as starting with a function and recoding it as a function. With a periodic function, what we can do is we can recode it just in terms of coefficients an and bn. But part 1 is the transform. We're taking the information in f and storing it in just these coefficients. And then part 2 is the inverse transform, where if I have the coefficients, I can recover the original function. So I think we've said everything in these notes. We've noticed that the role of p has changed from the top half of this slide to the bottom. We've talked about how there's a lot in this definition. There's the forward transform in part 1 and the inverse transform in part 2. And we've said that, if we know the function on the interval from negative p to p, we know the entire function because, of course, it's periodic with period 2p. Okay, so this slide is just supposed to illustrate this. As I said before, what we're doing with this representation is we're going to build the function from this combination of sines and cosines. And so in this picture, I'm just doing the cosine piece. When n is equal to 1, we're looking at this piece. That gives us the black wave where you have this cosine, which you can see our cosine wave with period 2p. And then when n is 2, we double that frequency, or we cut the wavelength in half, and that's what's shown with this red wave, which goes through 2 full cycles in the period between negative p and p. And then when n is 3, we have the blue wave, which goes through 3 full cycles. And we can reconstruct our periodic function with if I include more and more of these waves, I can get a closer and closer representation to the original function. And if I include all of the waves, as we do here, we recover the function exactly. Okay, so I think we've said this, that the ANs control the amplitude of the cosine waves, the BNs control the amplitudes of the sine waves. The A0, which I kind of neglected, but that controls the overall mean, and so that would shift things up or down. And on homework 4, you will do this. You will start with this, the periodic extension of this function. So what I've drawn here in black is the cosine curve from negative 1 to 1. Of course, we haven't done the full cycle of the cosine curve because we haven't dropped below the horizontal axis, right? If I do the periodic extension of that curve, what I have to do is I say, okay, I'm going to extend this curve, making it periodic, so that's the red bits. And so what we're going to have is this series of hills, but with no with no valleys that drop below the x-axis. And you'll find the formula for the ANs and the BNs, and you'll construct the series where it's truncated. So rather than taking it out to infinity, you're going to take it out to n equals 1 and 5 and 10. And what you'll see is that your truncated series will approximate this repeated periodic function better and better and better. Okay. So this, let me see here. The thing that's unique about Fourier series, remember we're in the Schabenberger and Gotway are going to approach this in 2 steps. They're going to talk about periodic functions, and then they're going to talk about non-periodic functions. With periodic functions, it only requires a discrete set of frequencies, and that makes sense because if I chose a sine or a cosine wave with a frequency that is not a multiple of 1 over 2p, then by including a wave of that frequency, I'm going to break the periodicity. I'm no longer going to have a period of 2p. And so I need to exclude waves without frequencies that are multiples of 1 over 2p. And so that's why we end up with a discrete set of frequencies. And so that's basically what I'm saying here, is that if we consider a cosine with frequency f and we enforce periodicity, then f has to be equal to n over 2p. And if it's not periodic. The jump to Fourier transforms, which we'll do a little bit later, is that all frequencies will be included, and so it won't be countable, it won't be a summation, it will be an integral. Okay, let me see here. Yeah, let me continue on for just a little bit more here. If this feels, I say this later, but let me jump to it now. I was just talking about the difference between Fourier series and Fourier transforms. We talked about how we start with a periodic function, we get to a coefficient, so that's the transform. It may not feel like a transform because it's not going function to function. It may feel more like a basis representation. What we can do with a periodic function is we can represent that function through a countable basis of sine and cosine waves, and that's what's happening here. We're recovering the original function by taking, this basically linear combination of sine and cosine waves. These are a useful basis for decomposing our original function. And so if Fourier series feels more like bases, that's fine. I think that's the right interpretation. And it's a nice basis, as I say here on slide 55, because it's an orthogonal basis. You can show that if I look at my basis functions, they're orthogonal. So if for any n and m, this integral is 0, meaning that our basis functions are orthogonal. If I take cosine times cosine and n does not equal m, I get 0, but if n equals m, this is equal to p. And so what we really have is this nice orthogonal basis where our basis functions don't interact with one another. They're orthogonal in this sense. Okay, so takeaway message: if we have a periodic function, and we know its period, of course, then there is a right set of basis functions. And we can get, and the basis functions are the sines and cosines waves, which have periods or frequencies which are multiples of 1 over the period. And the fundamental result given here says, we can reconstruct that function through this basis, but we have to get the right coefficients. And the recipe for getting the right coefficients is given here. We start with our function. We integrate it with respect to sine and cosine. That gives us our coefficients. And the way we're thinking of this recoding is we started with the function, we've recoded it as coefficients. And those coefficients contain all of the information of the original function. And I think that this homework assignment will help to illustrate that. Okay, so I will stop the recording here. This is just the first of several recordings which will cover Monday's lecture. So stay tuned for more.